How is everyone today? Oh, some names I don't recognise. That's always nice. Although I have to say, it is always nice to see names that I do recognise. Hi, Christine. Christine, did you understand what I meant about that moment? You know, with the forces. Great. Oh, and Christine, you're on panelists only. And I should say hello to YouTube. Hopefully it is working. I have told it to work. And is it? I'm just going to close YouTube because it's just going to be confusing watching both of them. So right, hello YouTube and hello non-YouTube. YouTube people, you are watching a stream of a class that I'm doing with my Tailored Tutors Maths A-level students. The first hour is going to be on hypothesis testing with the binomial distribution, and the second hour is going to be on the normal distribution, so a very statsy day today. I'm also going to be answering questions about TT revision method, study in general, how to improve your A-level maths grade, blah, blah, blah. But I haven't got YouTube open. I haven't got the chat open. I've only got the chat from the Zoom room. So if you do want to talk to me, then please join in the Tailored Tutors free trial, go to the Maths Live Classes page, and you'll see the chat that's going on. So if I'm answering questions and it looks weird and you're in YouTube, that's because I'm answering the questions from the Zoom. Hi everyone. If you are in the Zoom and you have your comments on panelists only, then only I can see, whereas if you change it to everyone, then students can see as well. Okay, let's go. So we're going to start with hypothesis testing, and I am going to begin by showing you what I would recommend that you do if you want to revise a particular topic using Tailored Tutors. Okay, so let's say that we know that hypothesis testing is a problem in the first year. In the first year, you've only got one hypothesis test. It's for the binomial distribution. In the second year, you would get two other types. So you get correlation hypothesis tests and normal hypothesis tests. George, are a few pages missing? Oh, if there's basically, I'm sure I've put that one back in, but if you just put a comment on the page, George, and then I will see that as soon as we finish teaching here, and I'll fix it. That's the quickest way. So you would go to the content guide and you would have a look on the left-hand side. This is where I'd recommend that you start. And even if like you think, oh, I don't need to do revision on this, I need to learn it from first principles, I'd still recommend that you go here because this is everything on the binomial distribution, including hypothesis testing. And so these are all on the left-hand side, these revision packs. Then if you want to create a set of notes in half an hour, 25 minutes that covers the whole thing, you can use that top section, and there's a link there to the PDFs that you can fill in as you watch that. And that's a really nice place to start with revision because it reassures you that you do know everything, and it's not that you like need to do more flashcards or more learning or go back to the textbook. It's you've got everything you need. It's all in here. It's just the practice and the understanding of the method that we need to work on. This will be the section that you spend most time on in your revision. This is all the past paper questions from 2017 and 2018 new spec. I can't put 2019 and 2020 up. I'm so sorry. As soon as I can, I will, but at the moment it's illegal because the exam boards are saying that 2019 papers and 2020 papers are still locked. So we can't put the solutions up. But what this gives you is the opportunity to split them into the easy questions, the medium questions, and the hard questions, or split them into just AS questions, just A-level questions. Because of course, in the A-level papers, you get some AS questions. So if you're revising AS, you might want to look at all the AS questions, including those for A-level papers. So that's what that's going to give you. And then have a look down here with the all questions, have a look how often something comes up that says a type of word question, because what you might realize is that 50%, like here, maybe that's a third to 50% of the questions have got some word questions in them. And it's usually the same types that keep coming up. So it'll give you a really good idea of the sort of word questions. And then an activity you could do is to just go through and look at the questions that have got these word questions and just copy them down and make that into a revision guide for yourself on, right, binomial distribution, what word questions do they ask and what do the answers look like? And that will give you a really good extra couple of marks when you're doing your final exam. So we are looking at hypothesis testing today. So I've lined these ones up as tabs and we're going to have a look through them. But first, I'm going to go over the method, and this will be super duper quick, hopefully less than 10 minutes, more like 5, of what you actually need to know and what the common mistakes are. Okay, let's switch to the iPad. George has received, oh, I've got a cookie stuck to me. George has received a topic list, and there's one that says tangents and normals and determinant. Don't think that you've heard of determinant. I think you mean discriminant, not determinant. The determinant is something to do with matrices, which is not in the A level, it's in the further maths. So it's probably just, because mathematicians use determinant and discriminant a lot, it's probably just a mistype. I'm sure it means discriminant. You know, b squared minus 4ac, number of roots of a quadratic and all that sort of thing. Shania, when you say your page doesn't look like that, can you just check, because there was someone with this yesterday, not like this, obviously, this is my iPad, but the revision pack pages, they're in the content guide, not in the exam guide. So if you go in the content guide and look on the left-hand side, that's where the revision pack pages are. And if yours doesn't look like that, then yes, definitely take a screenshot and send it in. Yeah, in that case, take a screenshot and send it in either, yeah, put it in a comment and then I'll be able to see what you can see. Okay, here we go. Whistle-stop tour of the hypothesis test, what you need to know and what commonly goes wrong and what the common mistakes and misunderstandings are. So first thing I'm going to say, and this applies to the normal distribution too, is that it is very, very helpful. Takes me ages to persuade students to do it, but it is very, very helpful to have 2 statements when you start the question of what X is. The second one is the one that students do. X is binomial, number of trials, probability of success. But what is a success? Now, if you don't write this down, what a success is, what you're actually measuring, then the examiner can twist you a little bit and make you do things wrong. It can make you use X or P when actually you should be using 1 minus P maybe. Because maybe success is hitting the goal and the question is about missing the goal. And because you haven't actually written down success is hitting the goal, then you might start to use the wrong thing. Also, and I'm going to show an example of this later, there's these questions where things are in things. Yes, you should be able to see this. Can you see this that I'm writing? This squiggle? Good, excellent, yes. So that's what I'm writing on. So this is what I want to encourage you to do to start. X is the number of, and then you say what a success is. And then here's the important bit, you say out of how many trials. So that number of trials, that's just n, that's the n in the binomial NP, but by writing it down and by specifically saying what a success is, that means that in the question, if they change n or they change what a success is, that you will be less likely to fall for that trick. So really common thing, part A in the binomial, they do n is something, and then part C, they change n, but the student doesn't notice, and that's where it goes wrong. So hypothesis testing is a general topic. It's in AS with the binomial distribution, and it's in the A level with the normal distribution and the correlation coefficient, but the process is the same and the concept is the same. So that's my first tip, is to write down X in numbers. X is the number of this is out of 10 or out of 20. X is binomial NP. The null hypothesis is always the P that's in your distribution. That P there is always the same. And this is what the world currently thinks is happening. This is what we thought before. This is what somebody is arguing against. So there is a person, and this person is arguing against the idea that we know what P is, okay? So this person is basically the one telling you what they think P is. So they're saying, no, P is not that actually, P is this. Or in normal distribution, no, mu is not that actually, mu is this. Or in the correlation coefficient, no, there isn't really any correlation. There's correlation that's positive or negative. So they're the one arguing against that P. They might be saying, no, it's not that actually, it's way bigger. They might be saying it's way bigger than that, it's way smaller than that. It's not that, doesn't matter. For now, I'm just going to leave that like that and not talk about one-tail and two-tail tests, because the only place that one-tail and two-tail test matters is here. This is the only place, one or two tail. And what happens is that students think that the one or two tail thing affects what we do here, what we find out, what probability we find out, and it doesn't. So I'm going to come back to that one or two tail when we need it, which is not now. So here's our guy. He's saying, rubbish, it's not that, it's this. And now we're going to see whether or not we believe him. We're going to see whether or not there's evidence. So a big question for students is, am I supposed to be finding the probability that X is greater than or equal to something, or the probability that X is less than or equal to something? And the way that this is generally taught, and this is where the confusion comes in with the one and two tails, the way this is usually taught is that this matches this. So if this is bigger, and if this is smaller, this is smaller, which means that when we have a two-tail test, and this doesn't say bigger or smaller, it says not equal, students get really confused on what it is they're meant to be doing. Are they meant to be doing both? Blah, blah, blah. So I want to really reinforce here that this has got nothing at all to do with the alternative hypothesis at all. This could be anything, and what we do here would remain the same. The only place that it changes is here, alpha or alpha over 2 when we make the comparison. That's the only place. So how do we know whether to go less than or equal to or bigger than or equal to? What we do is we look at what's happened. So this guy, he's got some evidence for his claim. He's done the test. He's saying, look, I threw the dice 14, I got 14 sixes, 14. There's no way your dice is fair. So, or maybe he's going, I got 1 out of 50 throws, I got 1 6. No way your dice is fair. So he has got this result, and he is saying that that proves basically that this is wrong and that what he's saying is right. So that's the actual number being used as evidence. That's this guy saying, I think I've got enough evidence to say that this is wrong. Now, we can compare that with what we were expecting. This is something that links first and second years together in a way, because it's obvious second years, if you've got a normal distribution, that what you would be expecting is the mean. And it's the mean that we're questioning as well in the normal distribution in the second year. So we would expect the average length to be 1.3 if the mean is 1.3. And if it comes out much bigger than 1.3 or much smaller than 1.3, then that's weird. In the case of the binomial distribution, we're expecting the average to happen. If I've got 100 tests and the probability is 0.25, I expect 25 successes. And that number that I just did is the number of trials times the probability. That's what I would expect. And that, second years, you should know is the mean of a binomial. Because when you do a binomial approximation of a normal approximating a binomial in the second year, the mean is NP. N times P, number of trials times probability, is the expectation. It's how many you expect to happen. So have a look at your binomial distribution and just do a quick calculation in your head. NP is what we would expect. So that means if this is right and he's wrong, if this is right, we would expect NP. Now have a look at what he's found. Is it big or is it small? If it's really big compared to what we would expect, then this is what you calculate. If it's really small compared with what you would expect, that is what you calculate. Now the actual calculation, this is binomial distribution stuff. I'm just going to very, very quickly recommend that you use a number line. So for example, bigger than or equal to 14. Draw yourself, I know this probably seems totally unnecessary, but draw yourself out a little number line like this and put a box around what you want. Bigger than or equal to 14. And then that will help you just put the right thing in the calculator. Tiny aside for second years, this also really helps with the continuity correction when you're doing the normal approximation to the binomial, because look, if I want bigger than or equal to 14, can you see that line there of the box round what I want is at 13.5. So you don't have to think, should I add a half? Should I subtract a half? Is it bigger? Is it bigger? Just draw the number line, put a box around what you want, and then you can see where the cutoff is, 13.5 or 14.5. So really, really nice thing to use for this. Okay, now we get our probability using the calculator, and this is where we look back and see what he was saying, this guy. So was he saying, it's not that, it's way bigger? Or was he saying, it's not that, it's way smaller? Or was he saying, it's not that, which is the two-tailed test? If he's saying it's bigger, then you compare the probability to alpha, the significance level. If he's saying it's smaller, that's still one tail, you compare that probability to alpha, the significance level. And only when he's saying, I don't know, it's not that. I'm not claiming it's bigger than or smaller, it's just not that. It's changed, it's different. That's a two-tailed test. And in that case, we have to half alpha before we do the comparison. That's the only thing we need one or two-tailed tests for. That's it. Other than that, nothing changes. That is the only place where two-tail makes a difference. So two-tail is where P does not equal 0, in which case we use half alpha. And one-tail is where he's saying it's bigger than or it's less than, and that's where we just compare to alpha, and that's the only place we need it. We do not need it here. Okay, small alpha, he wins. Small alpha, tiny weeny alpha, he wins. So if it's a tiny, tiny weeny alpha, tiny weeny probability, smaller than alpha, then he wins. Yes, it is H1 wins. Otherwise, H1 does not win. If it's not tiny enough, H1 not win. So if you're him, you want a tiny weeny alpha coming out. It's based on the, yes, whether or not he wins is basically how tiny the probability of the thing happening. So I throw the dice 100 times and I get 36s. 36s. I wouldn't be expecting 36s because that's not a sixth of 100. So that's weirdly big. So I would be calculating what is the probability of getting 30 or more sixes out of 100 sixes. I'd find that. Now, if that could happen by fluke quite a lot of the time, still might be a fair dice. If that would happen by fluke 1 in a million, billion, trillion, like tiny amount, then probably it's not a fair dice. Probably I'm right that it isn't a fair dice. So the smaller the probability, the weirder the thing that happened is. And if it's really, really weird, if it's a tiny probability of it happening by fluke, then the more realistic conclusion is that this was wrong. So he is looking for a tiny probability. And the significance level is how tiny is tiny enough. So sometimes anything less than a half is tiny enough. Sometimes it's less than 0.1. Sometimes it's less than 5% or 10%. So the person setting the test sets the significance level, and that is their level that if you are smaller than that, then, and you're the alternative hypothesis guy, you have to get smaller than that. So he is hoping for smaller. Is it tiny? That's the question. Then we write our conclusion, and our conclusion has 3 stages. Stage 1, the comparison. So you literally write down 0.03 is less than 0.5. So maybe the significance level is 0.5 and this has come out smaller, tinier, weenier than 0.5. So you do the actual comparison of the two numbers. Imran's saying, so if the significance level is smaller than the calculated level, yeah, so that basically the calculated level, you want it to be small. If you're the hypothesis, you're that guy, you want it to be small. So when you calculate your probability, if it comes out too bigger than alpha, then sorry, you do not win. So we do not reject this. We only reject this if the probability comes out tiny, tiny, tiny. So tiny, tiny probability means that we reject H0, which is what you want to do if you're that guy. Not tiny, not small enough, probability. So your probability is too big, it's bigger than alpha, then you don't reject H0. Okay. In your conclusion, do you talk about rejecting the null or accepting H1? This is a very good question. And in all reality, it doesn't really matter. Although if you go further into statistics, then people will argue about the difference between rejecting H0 and accepting H1 and the fact that they're not really the same. But for your purposes, there's two answers to that. One, it doesn't matter. Rejecting H0 and accepting H1 from your point of view, basically the same. That's answer number one. Answer number two is that traditionally what we do in the A level and what we do in a lot of hypothesis tests is only talk about H0. We don't actually talk about H1. So we either reject H0 or we don't reject H0. Don't reject H0 or reject H0. Yes, Christine, alpha is the significance level. Mez, I totally agree with you. Drawing a little number line to visualize whether or not it is small. Yeah, I do as well. I sometimes draw a little, well, I think of it as a normal distribution one, but if you think of it like this, here's what you would expect. So the probability of that happening is loads, right? If this happens, this is weird, right? This is weirdly big. Weirdly big. And the way that we can find out how weirdly big it is to find the probability to the right. And the smaller that is, the further right I must be, the further away from the expectation, the weirder. So smaller, 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 the smaller I get in these two areas, the more I'm going to reject H0. So if I was close to the expectation and those areas were big, I'm not going to reject H0 because it's probably just a fluke that it hasn't come out exactly right. But as I go away from the expectation, weirdly big or weirdly small, those areas get smaller and smaller and smaller and smaller. So when we calculate that area, what we're actually doing is calculating how far away we are from what we would expect. So the smaller those areas, the further away from the expectation, which means the weirder the result, which means the more likely that H1 is right and we're actually going to reject H0. So small, far away, reject H0. So the conclusion must come in 3 stages. First, compare them. 2, reject H0 or don't. And then 3 is the context. Now, when you do this, you're going to get 2 or 3 marks for these 3 points. And when you do the context, use the words in the question. So directly quote this guy here, what he was saying, directly quote it. Because if you don't, you might lose this mark. So if you say 0.03 is less than 0.5, we reject H0, there is evidence that the shop is making more money. You lose a mark. Do you know why? Because you said the shop, not Bill's Bakery. Okay, it's literally that specific. There will be, if you look in the mark schemes, there's a word that's highlighted. And if you haven't got that word in your conclusion, like Bill's Bakery, then you don't get that mark. So use the exact words from the, it is, Jasmine, you're right. Use the words from the thing. Okay, let's have a go. So I have screenshot the questions that I isolated using the revision pack. And now I would go through and work on these. Doesn't matter how slowly, it's better to get them completely right. And then traffic light them so that when you go back, you can see which ones you've done and not done. So I will let you choose. I'll show you the first 3 and you can choose. So this is number 1 out of your choices. Got some plants and there's a new method, and then it's how many suffer from the disease. 2. He's got some plants. There's a lot of plants, isn't there? He's got some plants and some of them grow, and he tries a new different seed, and it's whether or not they grow. 3. Someone is playing a game that doesn't involve plants, and he might win the game. Oh, he's got a new method, so he thinks he's going to win the game more times. Well, Shania, I don't know yet whether they're one tail or two tail, but also it really doesn't matter. It's such a tiny, tiny, tiny thing. The only time it matters whether it's one or two tail is at the comparison stage. And at the comparison stage, it's do we compare it with 5 or do we compare it with 2.5? That's the only reason we need to know whether it's one or two tail, literally. So this one, are we going to compare with 5 or 2.5? And then that's the end of the discussion. Here, are we going to compare with 2 or 1? That's the only thing. No, that's the whole point of what I was saying here, that the 1 or 2 tail does not affect this at all. 1 or 2 tail doesn't change whether you're doing this or this. Doesn't make any difference at all. Okay, would you like plants with a disease? Or would you like Martin growing cucumbers? Oh, lots of votes for Martin so far. Or would you like Nasir playing a game? Martin growing seeds. Martin's very popular, okay. Right, let's see if we can use that structure. Can you see that, or you can still see it? We're going to use that structure to hopefully see that we can always use the same strategies, okay? Right. How did I say to start? Like this. Yes, you do need to define your test statistic, yes. And this is a good point, actually, which I forgot to mention. If you are OCR, and it's only OCR, you have to say this sentence. Okay, you have to specifically say what P is. So let's start. X is not the probability, it's the number. Good. X is the number. And if they ask you to define it and it doesn't say the number of, you won't get the mark regardless of what you've written. It must be the number of, and then you're defining success. Seeds that, whoops, that's way too many S's and E's. Seeds that germinate. And I'm going to specifically say out of 20. There are 20 seeds in the test. And if the examiner does a sneaky thing and does a part B where it changes to 50 seeds, I would notice and then I would redefine my variable. Okay, so that's me making sure I'm not going to trip up on any of the common examiner trips that they put in. X is the number of seeds that's germinating out of 20. P is the probability of an individual seed germinating. That's OCR only that needs that. So binomial is NP, and the probability of one succeeding is 70%. So we've defined it. Now we're going to write down what H0 and H1 are. This is easy peasy. H0 is always that the probability is as we thought it was. And H1 is what the other person is saying about P. Actually, I'll put it underneath because they're usually underneath. So what's the other person saying about P? This guy. Whoop, 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 whoop. Is he saying it's bigger than 0.7? Is he saying it's less than 0.7? Or is he, honestly, no one cares if it's 1 or 2 tail. Okay, don't worry about 1 or 2 tail until we do the alpha comparison. That's the only place it matters. Doesn't matter here whatsoever. Just look at what he's saying. This guy is either saying more than that germinate or less than that germinate, or you're wrong, it's not 70%. So what's he saying? Here it is. They are more likely to germinate. Yeah. So just think about what that person is saying. Don't worry about this whole tail thing. It really becomes a big issue for students, and actually it really shouldn't be. I wish that we didn't teach it at all, because it starts to cloud the structure that's always the same. This guy is saying it's actually bigger than 0.7, but that's kind of irrelevant. We're only putting that down because we get a mark for it. Now we're going to find the probability. Okay. You always have the line, you always do a non-strict inequality there, always, always, always. And you always, always, always do a strict inequality here. This has to be, I think it's bigger, or I think it's less, or I think it's not equal. Here, it always has to be a non-strict inequality, always, always, always. Okay, so how many are we expecting to germinate? Let's go n times p. We're expecting 70% of 20. 14. Oh, that's why you said 14, Shania. Yes, we're expecting 14. Correct. How many actually germinated? Oh, 18. That seems big, right? How big? Don't know. We need to see how far away from 14 it really is. Now, 18 is weirdly big, not weirdly small. So that means that we are going to find the area to the right to find out just how far to the right it's gone. Is that area quite big, or is that area tiny, tiny, tiny? So that is what we're going to find out. Okay, grab your calculators. I'm going to do it in silence while you do it. Let's find that probability. Naught 0.035. Okay. Yes, exactly, May. So I need, this is the useful thing about the box, I think. I want this. The whole thing adds up to 1. The calculator only does less than or equal to. So what I need to put into the calculator is less than or equal to 17, and it only does less than or equal to. And then 1 minus that bit is that bit. Bruce, did you make the mistake of doing, did you do, in your calculator, did you do the probability that x is less than or equal to 18? Because it should be 17. Yeah, that's a very, very common mistake. So the number line is super duper useful for never making that mistake. It's a very, very common mistake. And all it is you chuck down a line and put a box around what you want, and then it's obvious what to put into the calculator. Christine's saying, I don't get what the significance level is used for. We haven't used it yet. We haven't used this guy at all yet, if you think about it. The reason that I did bigger than is because 18 was bigger than what I expected. Now I'm going to use it. So am I going to compare with 5, or am I going to compare with 2.5? This is where we go and see what he said. And if he said bigger or less, then we go with the 5. If he said, don't know, just not 0.7, it's changed, it's different, then we use 2.5. And that's it. That's the only 1-2 tail. That's the only thing that makes any difference. So this guy said bigger, He didn't say not equal, he said bigger. So that means that I'm going to compare it with 5. So 0.035, that is less than 0.05. So what does that mean? It's really teeny, yeah? Tiny. Excellent. Tiny, tiny, tiny. So we reject H0. And then we write our sentence, and our sentence will be the following. Where's his claim? There is not, oh, we are rejecting H0. There is evidence to suggest that, and now we need his specific claim, that this brand, no, that these seeds are more likely to successfully germinate than other brands of seeds. This is the final sentence. Okay, I'm just going to have a look at what questions. Don't we need to do not equal for H1 when it's two-tailed? I honestly, can you see that most of the questions here are about one or two tail, and that it's one or two tail that's causing the bother? So what I would recommend that you try to do just for the next few questions is to literally forget one or two tail, forget it completely. Pretend you've never found any, never heard of it, right? What's written down here is what the guy is saying. So is the guy saying it's bigger, or is the guy saying it's smaller, or is the guy saying, I don't know, it's changed? If he's saying it's bigger, put bigger. If he's saying it's smaller, put smaller. And if he's saying it's changed, put not equal. So just put here what he's saying, what he's claiming. When you come to the conclusion, this is where you have to have a little look. So when you come to the conclusion and you're doing your comparison, you can't just compare with 5. You have to have a little quick look about what he was saying. And if he said not equal, didn't say it was bigger, didn't say it was less, just said, I think it's changed, then you do half of that. And if he's saying it's bigger or smaller, then you do that. That's it. Yes. That means that this is the critical region is when that's small enough. So the critical region is all the places where we would reject H0, where this guy's claim, yeah, you're right, that's really weird. So there'll be a point here where that area there is 5%, and anything in there, we're going to reject H0 because it's tiny. And tiny means less than the significance level. Really, with this topic, it's the language that's confusing, not the actual maths. There's so much language around it that it seems like you really have to deeply understand something, whereas actually it's pretty standard, same things every single time, and not that much thought really needed. Yeah, so tiny means it lies within the critical region. One tail. Oh, other way around, Mez. So tails are the ends. And one tail means that the guy making the claim thinks he knows which tail it's in. I think it's in the right-hand tail. I think it's bigger. I think it's in the left-hand tail. I think it's smaller. So if I say I think it's bigger, I'm specifically saying it's in that tail, one tail. If I say smaller, I'm specifically saying that tail, one tail. If I say different or changed, then I'm not specifying which tail, so two tail. But have you seen any questions where it says, is this one tail or two tail? Because I haven't. Have you seen any questions where it says, explain how you knew to half? No. I haven't seen the word tail in any question or mark scheme. So it's the language that we use, but if it's not helping you to understand and it's actually creating more layers of confusion, then let's try just removing it. So here, just write down what the person said. And here in the comparison, why is my little pointer not working? Is the pen working? No. I'm just going to unshare and share again because I think it stopped sharing. Sorry. Right. Any more questions on this one before we try another one? Because I think it is in the doing of them that you really see how the structure works of the solution. So May says, when do the upper tail and lower tail come into play? Good question. They come into play right down here when we do the comparison. So when we do the comparison, we're saying, is that area small enough? Am I far enough away from the expectation? Am I in the critical region? So the tails are the critical bit, which you can make as small as you like using your significance level. And then when you do that comparison, you're saying, am I small enough? Am I far enough away from what we would expect? To find the critical region, do you do the inverse for 5%? Yes, Sophie, exactly. So yeah, we can do one of those if you like, where it's the same principle, but instead of the guy saying, so this guy, he says 18 of my seeds germinated. Is that enough for you to believe me? The other question that this guy can ask is, I'm about to plant my seeds. How many would have to germinate for you to believe me that my seeds are better? So that's where you're saying, I haven't got 18, they haven't germinated yet, but before they germinate, I want you to tell me what would be enough. When would you believe me? That's what the critical value is. Do you know, you know significance level, does that mean the probability that the seeds germinated better than other brands due to chance? Yes. So whenever you do anything, you can get a really weird result. You can toss a coin 100 times and get 100 heads. That does not mean it's a biased coin. That's just reality. It's extremely unusual, but it could happen. So when we're up here in a tail or down here in a tail, we're going to reject the null hypothesis. We're going to reject that the probability is actually 0.7 because something really weird happened. Now, if you're in a medical situation and you're going to decide that a treatment is or is not a good idea or is not working, that's really dodgy if it could have happened by fluke. And there's a really famous case where a woman was sent to prison because 3 of her children died of cot death. And the only reason that they had to convict her was that 3 of her children died of cot death. And what they said was, for this to happen by fluke would be 0.02%. Therefore, it wasn't fluke. Therefore, she murdered them, which is obviously not true. And years later, she was let out because actually there's more research into cot death. And actually they found that there is a genetic effect in the thing. So actually, yeah, but that was it. That was the only thing that convicted her, was that the thing that happened was unlikely. Therefore, it couldn't have been true, which is very dodgy. In my calculator, you can do the binomial CD, and then the probability with the lower bound is 18 and the higher bound is 20. Yep, that's all. That's fine. Yeah, if you can find the probability, if your calculator does 18 to 20, like that, then you are finding straight away what you want. That's totally fine. Yeah. So we want P, May, to be as tiny as possible, or rather this guy wants P to be as tiny as possible, because then H0 is rejected. Yusuf, yep, you're quite right. If he had said changed rather than improved, then we would have a not equal to here, which would mean that we would be comparing with 2.5, not 5, which would mean that this was 2.5, not 5, which would mean that that wasn't tiny enough, which would mean we would not reject H0. Correct. What are the 4 requirements we need to be able to use hypothesis testing? It's just about the binomial. It's nothing to do with hypothesis testing. It's that when you do hypothesis testing, you're assuming that this data can be modeled binomially. So do you know the conditions for this data to be modeled binomially? So you have to have got a random sample. The sample must have been random. N is fixed, P is fixed, the trials are independent. Isn't there another one? N is fixed, P is constant, the trials are independent. And the sample is, it's the 4, I know there's 4, and the sample is randomly, I think it's that. But it's nothing to do with hypothesis testing, okay? To use a hypothesis test, we have to use a binomial distribution, a model, a normal distribution or a binomial distribution. So therefore that question, what are the requirements, is actually saying what are the requirements for a binomial distribution to be appropriate, or what are the requirements for a normal distribution to be appropriate. Okay, critical region. Let's find one with a critical region. So this one isn't critical region because he won 16. So he's saying, I won 16. That shows that I'm the best. This one, here we go. Here we go. So this one is saying not, sorry, I put that a bit too high. This one is saying not that we've done it. I'm the person, I'm Bryony, and I'm saying like, I did it and this is how many I got. Do you believe me? That she's not saying that. She's saying, how many would I have to get for you to believe me? That's the rejection region. That's where I would reject H0. So Bryony wants to know in advance how many she would have to get in order to reject H0. That's what she's saying. Okay, so let's have a go at this one. So I'm going to do my usual start. I'm going to see what X is. Six-sided dice biased. So it's the number of twos on a dice out of 35 throws. And that really pins us down to exactly what we're looking at. X is binomial, N, P. Now, if it's not biased, P will be a sixth. Okay, H0, P is a sixth. H1 is what Bryony is saying. Okay, now I'm just going to leave that for a minute because I want you to see how irrelevant what Bryony is saying is for the next stage. So what were we expecting here? Number of twos. So we're throwing it 35 times and it's a sixth each time is what we'd expect. So 1 divided by 6 times 35, N times P is 5.83. That's what we'd expect. Now, what is it Bryony's saying? Is she saying that it's biased in favor of a P? So she's expecting to get more than that or less? She thinks it's biased in favor of a 2. So she is saying that the chance of getting a 2 is bigger than a sixth. She's saying that she expects to get more than 6 twos when she throws it. She's expecting to be up here somewhere. Now, what we want to find out for Bryony is how many twos does she have to get out of 35 for us to reject H0? Now, we know we'd reject H0 if this probability came out really small. What does really small mean? It means smaller than the significance level. What is the significance level? 4%. Do we compare with 4 or 2? 4. Exactly, because she's gone specifically one way, so it's 4, not a half. So when does this become 4%? That's the question we need to ask. In notation, it looks like this. The probability that X is greater than or equal to some number that we're trying to find out has got to be smaller than tiny this. That's what we're trying to find. We're trying to find when it gets tiny. But that's kind of confusing, that sentence. I would prefer to just find some probabilities, okay? And you don't have an inverse button on your calculator, so let's just try some. So what do you think? It's out of 35. We're expecting 6 twos. How many twos do you think, what would be your guess at what that number is? And it doesn't matter if it's a wrong guess. Yes, you can absolutely do the list function in binomial. Yep, you can do trial and error, or you can do the list function in your calculator. Yeah. So what we're trying to find is if she gets this many twos when she throws the dice 35 times, instead of every time doing a hypothesis test, she wants to know in advance. So she wants to know, how many 2s do I have to get out of 35 for you to believe me that I'm right when I say that the dice is biased? 10. Let's try 10. While I'm trying ones, if you know how to do the list function, you do that and then we'll get the answer. So I'm going to do the probability that it's greater than or equal to 10. Oh, I literally just typed, well, I didn't type that in. I did my number line. I want greater than or equal to 10. So did I do it right? Did I do that right? So I didn't actually write my number line down. I wonder whether I did it wrong. I'm going to do the probability that x is less than or equal to 9, and then I'm going to do 1 minus. Oh, I did do it wrong. I did the same mistake as I pointed out last time. Actually, that shows how important it is. I didn't draw out the number line. I made the exact same mistake that I pointed out last time, that it's not the probability it's less than or equal to 10, and I made that exact same mistake. Okay. Is that less than 4? No. I'm trying to bump it up so that the area to the right is tiny, and tiny means less than 4. So 10 wasn't far enough to the right. So let's budget up a little bit and try 11. And if you've got this list, then you can see straight away which one is the one you want. So let's try 11. So now I am going to do the probability that it's less than or equal to 10 and then do 1 minus. Is that smaller than 4? Zeph, it has to be smaller than the significance level unless it tells you you can be as close as possible. So sometimes what we do is just in the question, it says, don't worry, you don't have to be smaller than it, just be as close as possible. And if it doesn't specifically say that, then we need to be actually smaller. Yeah, that's right, Bruce. I'm trying to see how far away from what we would expect I need to go in order for this area to become less than 4%. So the further away I am from 6, the weirder the result is, because we would be expecting 6 2s out of the 35 throws. And if I get further and further and further away from that, the chance of that happening by fluke gets less and less and less. And we want to know which is the first one where it becomes less than 4% likely to happen by fluke. And the first one is 11. So you're quite right. The critical region, or the rejection region, these are the number of 2s that I could throw in order to then say, she's right, Bryony is right. Now, here's an important bit in terms of exam technique. This is needed. So if you do it on your calc, say you hit 11 straight off and went, oh, brilliant, that's less than 4%. You still need to check 10, because maybe 10 is less than 4% as well. Maybe 9 is. So you have to find the one which is not in the critical region to show that the one that is in the critical region is the first one in the critical region. So you do need to state the one that isn't in the critical region as well as the one in the critical region. Okay, so we've gone through in detail a a critical region 1 and a not critical region 1. And May, you're completely right. The actual significance for the test is 0.23. Yeah, that probability there, that is the actual significance, which is the probability. They could ask this, it's the probability of incorrectly rejecting H0. So anything up here, 11 or more, we're going to reject H0, but we might be wrong. It might have been a fair dice all along. Poor little dice, totally fair. You roll it 35 times, flukily, you get 11 twos, but it's just a fluke because flukes happen. And then because you got 11 twos, you're thrown in the bin as a biased dice. You weren't biased at all. So that 23% there, that is how often we would reject the dice, reject H0, even though actually H0 is right, it is a fair dice. So it's the actual significance is the probability of incorrectly rejecting H0. Yes, the region on the right, that's the critical. Well, this is the critical values, 11 and more, and that area is the critical I think this is also called critical region, is all of the X's, 11, 12, 13, 14, 15. That's the critical region. That area is the significance level. And that area is the probability of incorrectly rejecting H0. Whew. How do you feel? Good. So let's go back. Let's finish off by going back to the revision page that we were on. And we'll go through and you're going to see the questions that you did. What did we do? We did Martin's cucumbers, we did. So we'll put that one as green because we've done Martin's cucumbers. And then we did Bryony's dice. And that one was okay, but maybe that's it. Oops, there it is. That one's okay, but maybe I'm going to put that one amber because it's difficult. And then that means that when you go back to the binomial distribution to do your next action hour, you can see which ones you did, and you can see whether or not maybe you want to avoid ones you've already done, or go back and do your reds and ambers or whatever. So Bruce, try out an action hour using this revision page. So who was it is asking about normal distribution? I'm not being examined on year 13 stats. So do you think I should stay for the second session? No, because I'm just going to be doing normal distribution. And normal distribution is second year stats. So if you're not being assessed on that, then yeah, go do some more work on TT revision method and go from there. I didn't know that you could see what other people have done on the Forest app. I thought it was just you that you could see. I used that for a while. Oh, you added each other. Cool. That's actually a really good idea because you can be sort of a study buddy with each other, can't you? And keep an eye, like we both, like say we're going to do an hour between 3 and 9, and then the other person, yeah, hold each other accountable. Exactly. So this page, I'll put a link in the chat. See if you can get it there. It's in the content guide, left-hand side, maths revision packs. Oh, I sent it to myself. Brilliant. There you go. Let me know if that doesn't work. Okay, I'm going to switch to second years now. And it's 2 o'clock, and talk to second years about normal distribution. No worry, Jasmine, I'll see you later. So normal distribution. This used to be a really hard topic because you weren't allowed to use your calculator. I've just realised my computer's on a low battery. You weren't allowed to use your calculator to find the probabilities. Hooray, yes, exactly. But now we have calculators. But this is a little bit like what's it called? Algebraic division. You used to have to use polynomial division, algebraic division. It's like a bus stop and things go down. You used to have to use that because you might be dividing by a quadratic. So we taught that because you had to use it. New spec, they're not going to be dividing by quadratics. You're only dividing by linear. So that means that you don't have to use that method. You can use synthetic division, which is much, much easier. But teachers looking at it will have looked at the new spec and say, all right, we're still doing division. We're still doing factor theorem. We're still doing that stuff. So they're teaching it the same way they used to teach it. So most teachers are still teaching algebraic or polynomial division. And actually, I think that's, well, already we see when we're doing marking that it's slowly tipping over towards synthetic division or equating coefficients. So I think what's going to happen slowly over the next few years is that teachers will realize that, number one, they don't have to teach polynomial division, and number two, students make lots of mistakes. So do teachers when we're doing algebraic division, so they'll stop teaching it. And it's kind of the same thing with the normal distribution. Because we used to teach it that you had to use Z, the Z01, the standard normal, we had to teach that. You always had to change X into Z because you were using tables. There seems to be a lot of teachers that are still teaching that you always need to change X into Z so that you can then use your calculator. And you don't. You don't, because you're allowed to use your calculator for X. So the way that I'm going to split this up for you is to talk through the types of questions and what you need to know for each type of question and the general technique that you would use to solve those types of questions. And then we'll have a look at some specific questions. And obviously, feel free to ask questions as we go along. If you're in YouTube, then bear in mind that I can't see what you're saying because I haven't got YouTube chat open. I've only got the Zoom chat open for the students in the room. You can join in the room totally free. You can have a week free with the Tailored Tutors free trial, then go to maths live classes, and then you'll see the link to this class, and then you'll be in the room. So you'll be able to see all the same things, but you'll also be able to see the chat. Okay, so here we go with the normal distribution. There are three types of questions. One type of question is where you know the mean and you know the variance. Another type of question is where either you don't know the mean or you don't know the variance, or both. That's a really important distinction. And then the other type of question is when you're doing an approximation to a binomial problem. So this is when you can only use this when n is big and p is roughly equal to a half. Now that's not the best test for whether or not your approximation will be good. There's other tests you can do, which you may have seen. NP is bigger than 5 and NP1 minus p is bigger than 5. That's a standard test. But the one that is mentioned in the specification, the one that you will probably use, yeah, how big is big and how close is close? Really, you don't need to know, because the question will say approximate or it will say estimate. So you'll know that it's expecting you to go and use that approximation. Approximate or estimate means that you're going to be using an approximation. So really the only reason for knowing that n has to be big and p has to be small is if they say what are the conditions, and then you say n is big and p is close to a half. So you know those because they might test you, rather than the idea that you would have to go and, you know, work out whether or not it was appropriate for you to, I don't know why I can't rub that out, never mind, to do it. So type 1, we know both of them. Type 2, we don't know them. Type 3, a binomial that turns into a normal. Key features. Now, this is a different type of question that they never used to ask. So when you're doing past papers from before new spec, before 2018, you won't see, I think any questions on the features. Maybe occasionally it's brought in, but it's much more common on the new spec. So what are, Imran, yes, you raised your hand. So what are the key features? They're literally that's the mean. So if they give you a picture, that high bit is the mean. And then the other key feature involves looking for an inflection point. So I'm going to remind you, and this is pure maths, but I'm going to remind you what an inflection point is. An inflection point is a point on a graph, any graph, where the graph changes from convex to or from concave. That's what an inflection point is. Concave is where the second derivative is negative. Convex is where the second derivative is positive. So it's where the second derivative switches from negative to positive, but we don't need to work that out with a normal distribution. With a normal distribution, we just need to know what those words mean. So concave is where if you join up two points, the line is underneath. Convex is if you join up 2 points, the line is on top. And the normal distribution does this, look. This bit here is convex, and then this bit here is concave. That bit there is concave, that bit there is convex. Exactly. So somewhere along here, there are inflection points. And what you need to know is that those inflection points are always at the mean plus or minus 1 standard deviation. So this distance is 2 standard deviations. That's basically it. The only other thing that they sometimes want you to know is like, for all normal distributions, how much data is, or how much probability is there between minus 1 standard deviation to plus 1 standard deviation? How much is there if we go from minus 2, that's not, I wrote that wrong, mu minus 2 standard deviations, mu plus 2 standard deviations, how big is that? And 3. Mu minus 3 standard deviations, mu plus 3 standard deviations, how big is that? Does anyone know those numbers? Excellent. First one, 68. Second one, 95, good. And the last one is basically 100. It's like 99.7, yeah. It's basically 100-ish. So one of the questions that they ask is, like, here's some data. Would it be a good idea for me to use the normal distribution to model this data? And you can say, well, is it symmetric? Is it just as likely to be small as it is to be big? Because that's a key feature, the symmetry here. Is 100% of the data within 3 standard deviations of the mean? Because that's a key feature of a normal distribution. So if the data goes like some outliers above mean plus 3 standard deviations or below, probably not normal. Or like this one, 68%. How much of the data is within 1 standard deviation of the mean? Is it about 68%? If so, probably good to use a normal. If not, no, because normal distributions always have 68% of the data within 1 standard deviation of the mean. So that is the key features that are sometimes tested. If you know mu and sigma, you just stick it in your calculator. I recommend always drawing it and not doing your asymptote the way I just did that asymptote, because that's a rubbish asymptote. It should be same as a graph, asymptotic like that. And then just draw on what you want. Here's the mean. Here's the thing that you're finding out about. Maybe you're doing less than, maybe you're doing bigger than, but a picture just guides you not to make common mistakes. Really quick, really simple, just where am I relative to the mean? Am I looking to the right or am I looking to the left? And use that picture instead of the confusing notation. If you don't know the mean or you don't know the standard deviation, you're doing exactly the same thing, but you can't put it in your calculator because you don't know the mean or you don't know the standard deviation. So when it goes in your calculator, the mean has to be 0 and the standard deviation has to be 1 because we've changed the question to being about Z. And that's why we change it to being about Z. But it's the same picture. Here's the mean of your distribution. Here's the thing that you want to find out about. Maybe we want to find the area to the right. And all you have to do is find the Z to put into the calculator. And lining it up like that, having that picture that shows what you are trying to find, if we were in the scenario bottom left where we do know the mean and we do know the variance, that's what it would look like. And then just one more axis which shows where Z is relative to X. And it just keeps everything really controlled on that page. And it means that you're unlikely to slip up, not because you don't know the topic or you can't do it, but because there's so much notation and a sign flips accidentally and you're trying to remember whether you want to do 1 minus or not. Or so the pictures really control all of that. And then all you have to know is the formula. Z is whatever X is minus the mean divided by the standard deviation. So if you know that, you can move between the two. When you're doing the approximation, you change 2 things. You change your binomial into a normal, and you change your binomial question into a normal question using the continuity correction. Now, AQA have decided not to test the continuity correction because the specification says students need to be able to use the normal approximation to approximate the binomial problems. Okay, Christine, yes, PD and CD are for N are the same as PD and CD for B for binomial. So the continuity correction is not AQA. So if you're AQA, you would literally just calculate that for this normal. If you are not AQA, you need to use the continuity correction. And this is something that, again, yeah, this is where you change 3 to 3.5 and you change 5 to 4.5 or 5.5 or whatever it is. And this is something which students have these like really complicated, if it's this, do this, if it's this and this, do this, if it's this, do this, and gets in a right model. If you use your number line, which I suggest for the binomial, it's so obvious. So look, think of this as a binomial problem. 1, 2, 3, 4, 5, 6, 7, blah, 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 naught. Which ones do I want? I need to be bigger than 3 and smaller than or equal to 5. Now just imagine a number line. You've already got the limits of what you want. Your box is already round what you want. So you can just look at that box and see that the box goes from 3.5 to 5.5. So that's what you would put in your calculator. So we've covered key features, main things that you have to know, facts, and you might have to use. The fact that if you know mu and sigma, you definitely don't need Z, you just stick it all in your calculator, and that I recommend pictures. That if you don't know mu or you don't know sigma, so you're having to use Z, then I recommend this double axis thing so that it's all connected and really clear. And that if you do an approximation to the binomial, then don't forget that as well as changing the binomial to normal, you have to change, unless you're AQA, you have to change the question to a normal question by using the continuity correction. So it would change to this with that continuity correction. Okay, should we try some questions? Or has anyone got anything that they would like to add? They think I've forgotten or you're not sure about? The simultaneous equations come in, Imran, when you don't know mu and you don't know sigma. because to find two things, you need two equations to do simultaneous equations. You like them. I don't, because I don't like doing simultaneous equations. And the whole of mechanics is simultaneous equations. And in stats, you don't really use simultaneous equations until you get to this topic, and then it's simultaneous equations. And I don't know, they're just messy and they have numbers in, and I just don't like them. Yeah, I know how to do them. I just don't like doing them. I go wrong. That's why I get angry. Like partial fractions, I can do partial fractions. Can I do partial fractions without going wrong? No, because you have to use equations and numbers to find the A and the B, and I just always go wrong, always. It's almost like I can't actually do simultaneous equations without going wrong, no matter how hard I try. So I just get angry, and I don't think it's fun. I just like, my favorite thing is solving differential equations. I could solve differential equations all day, very happily. Yeah, very happily. I'd be a happy person if that's all I did with my life. Right, this is the wrong page, isn't it? Because this is not normal distribution, this is binomial. Here we go. So we start off on the normal distribution revision page. There are some notes there, 25-minute lesson going through the whole thing, and some notes to print off so that you can fill in to make it easier. If you want to drill down into more lessons, they're all here, specific lessons on specific things, and there's some resources, and there's the whole course resources there as well. These are all the questions that have been asked recently. You can split them into easy ones. There's only two, medium ones and hard ones. You can use the all to see what sorts of exam questions they ask, like word ones, give reasons for. So sometimes there's like 3 marks there. So it could be half the value of the question for these word questions. So getting used to those, maybe click on these ones, print those off, and like write down the word questions to see the patterns and the similarities. Okay, so I have screenshot the normal distribution questions that don't involve the hypothesis test. And I'll show you, there's 5 of those. I'll show you a few and you can choose which one that you would like to do. You see how exam boards are going to release exam materials. Are we going to release the 2020s? If we're allowed to, we will. We've done the 2019s and the 2020s. But we're not allowed to release them. But basically, as soon as I get that stuff from the exam boards, then yes, I will be doing sessions on them and doing video solutions to them immediately. Yeah. Imran, I'd love to. They're all done. All I'd have to do is push a button. But I'm not allowed. I think you're allowed to ask me about them. So if you screenshot one and ask me, I can help. But I'm not allowed to put the paper up and put the solutions up. Okay, here we have a question. I'll give you 3 that you can choose from. This is one where you do a bit of normal stuff, then you do a bit of normal backwards normal stuff, then you do some in-betweeny stuff. So this is quite a nice gentle introduction to when we know the mean and we know the variance. And then we've got this one that looks really difficult, but actually isn't. We don't know the mean, we don't know the variance, and we're being asked a question. So it might be that we need to go into the Z for that, maybe not, depends. I'm going to draw a picture, and the pictures always guide me in what I need to do. That's option 1, and this is option 2. I'm just going to give you 2 options for this one. So this is where we've got some actual data, and they're testing the special features. Why might it be reasonable for us to use the normal? So you have to know the features of the normal so you can compare and see whether or not it matches. Then we've got standard, between 2 things, standard, smaller. So this one is all about knowing the mean and knowing the variance. So there's not going to be any use of Z in this one. But there's this funny data, and there's these word questions about the data. So would you like number 1, no word questions, standard practice of normal distribution, or would you like number 2, again, a little bit of standard practice and some word questions? 1 is popular. One is popular. Okay. Don't forget these word questions though, okay? These word questions account for a decent number of marks when you add them up. It's more than you'd imagine. It's a decent number of marks. So actually getting good at word questions is worth more marks than getting good at range and domain, for example. So try to get some marks from there as well. Don't do what we all mathematicians do and just go, oh, just blag it, just write something boring. Don't know, what do you want me to write? That, yes. Word questions are horrible, but they're very samey. When you actually look at them, there's only actually a few word questions. I might make you a pack of like, what word questions do they ask and what answers do they want? That'd probably be helpful. Okay, so probability that x is bigger than 25. I always start with my picture. The mean is 20. 25 is bigger. It says I want the area to the right. And then I get the calculator. Yeah, they seem different, May, but they're not. Which is, it's good when you start to realize that they're not, that they're the same every time. Okay, so x is 25 and, oh, I'm in binomial. Tell me if you get this before me. Just to check, because I was talking to somebody earlier today actually about the lower bound here, like what lower bound and upper bound do we put in to get the right answer? So the probability that x is bigger than 25, 3 significant figures, 0.048. No, that is 2 significant figures, 0.0478. Why have we got different, May? This is the standard deviation, not the variance. So you should have put in that the mean is 20, standard deviation is 3, the lower bound is 25, and the upper, you just have to put a massive number. Yeah, that's what I put, Mez. 1,000 million or something. Okay, part B. Picture, mean. Don't know A, but the area to the right is 0.2. So is this a possibility? Or could it be this? Not that it matters, but it might matter if we don't know things. We might have to think a little bit more. It's definitely going to be inverse normal, yeah, because we're finding an x value from a probability, but just in terms of which of those pictures is it? So is it this first picture or is it this second picture? Because we might need, getting good at drawing these pictures and understanding the connection between the notation and the pictures is really helpful when it comes to stuff like this that looks really difficult. It's definitely to the right that we're shading, agreed. It's definitely to the right, but I've done that on both. So I shaded to the right there and I shaded to the right there. So it's to the right because it's greater than, but which of those two pictures is correct? The number that I'm trying to find, A, is it bigger than 20 or is it less than 20? But obviously I'm going to find it in a minute, right? But before I find it, I know whether or not it's bigger than 20 or smaller than 20. So have a look at those pictures. One of them cannot possibly be true. The other one must be what's going on. And these pictures really help when it comes to the part C's. And the answer is that number 1 is the correct one. The mean is 20 here. That's the mean of the distribution is 20. So 20 is in the middle. The area to the right, so I've shaded to the right, but this can't be 0.2. The whole thing, oh, I see what you mean about the half. Yes, all of the area to the right of 20 is equal to a half. So this whole bit here is bigger than a half. There's no way it's 0.2. It's bigger than a half. So just by knowing those things about the normal distribution and the fact that half the area is a half, it means that this is the picture. It has to be this. This is the picture here. And the thing down the bottom that we're trying to find, that's A, and it's definitely bigger than 20. So now we stick it in the calculator. Inverse normal. Okay, now on these, when you do inverse normal, it only does the area to the left. So, oh no, that's not true. No, that is true. Does it only do the area to the left? Inverse normal. Yeah, it says area on the calculator, and the area is always the area to the left. So when it says area, you're going to say 0.8. When it says mean, oops, it says standard deviation first. Standard deviation, 3. Mean, 20. And the answer is 22.52. 22.5 to 3 significant figures. Okay, last but not least of these easy ones where we're just drawing a picture and then that's guiding us in what we need to do. Draw a picture. 20 in the middle. 20 minus B. 20 plus B. Notice that that distance and that distance are both the same. The area between these two is 0.5. Right, how are we gonna find B? It's definitely nothing to do with Z. We know the mean is 20. We know the standard deviation is 3. It's nothing to do with Z. It's definitely to do with just sticking it in the calculator. Yeah, inverse normal. Whenever we're finding anything on this axis, it's the inverse normal that we need. So we're going to go inverse normal. Now, here we have a problem because inverse normal only does the area to the left. So if I put in a half for the area, I'm just going to get 20. So what should I put in? Excellent. This is 0.25 and this is 0.25. So for the area, I could do 0.25 or I could do 0.75. If I do 0.25, I'll come up with this. And if I do 0.75, that's this area. This area here is 0.75. So then I would get that. So the picture really makes it clear what you need to put in. So I'm going to put in 0.25. And that is going to get me my 20 add B. No, 20 minus B. So then you can get the answer. How's that seem? How does that seem for these top ones? Yeah? It really is picture calculator. And it's the picture that tells you what to put in the calculator. The same as with the binomial distribution, it's the number line picture that tells you what to put into the calculator. Now, I'm going to have a look at II now because that's a really interesting one. It's a totally new distribution. I don't know whether I don't know what's going on with it at all. It's got nothing to do with X, it's Y. It's a whole brand new slate. And I think I'm going to need Z because I don't know the mean and I don't know the standard deviation. But let's see, let's draw it. Because even if I do need Z, I'm going to draw it like that anyway. So I'm still going to use this picture. So I want the probability that Y is bigger than 1.5 mu's, mu being the mean. So 1.5 mu's, well, that must be to the right, yeah, because 1.5 of something is bigger than 1 of something. So this is 1.5 mu there. The question says, find the area to the right. So this is what I'm trying to find. So I need normal CD, not inverse normal. Inverse normal is where I'm trying to find the thing on the y-axis. This is where I'm trying to find an area. Okay. Now, this is nothing to do with like maybe if I'd gone mu plus sigma, then I could use my common facts about normal distribution, because I know that if I go forward a sigma and back a sigma, I get 68%. So then I can work out how much is on the right, all that sort of thing. This one is 1.5 mu, so I am going to change to Z. So this is how I do it. Just draw another line, and all of the Y's can change into Z's. And the way you do that is you take away the mean and you divide by the standard deviation. And the standard deviation is the square root of the variance. Yep, perfect, mu over 3. So let's simplify that Z value. 1.5 mu minus a whole mu divided by 1/3 of mu. Well, that's 0.5 mu over 1/3 mu, and they cancel, and that is 1.5. So this is actually just 1.5. And now that work has taken this question from being one that I couldn't do to one that I can do. And now it's the exact same method as this. Do you remember how we did that one? That's X. We had 20 in the middle. There was 25. We need the area to the right. We went into the calculator. We said that the lower limit was 25 and the upper limit was 1,000,000 billion billion, and that the standard deviation was 3 and that the mean was 20. And then we just pressed go. And this is exactly the same question. We go in, we say the lower bound is 1.5, the upper bound is 1,000,000 billion. The standard deviation is 1, the mean is 0, and we press go. And it tells us the area to the right. And then we've done. So this question and this question are exactly the same, except that for the second question, I had to know that formula connecting these two so that I could put that in my calculator. So just the only difference is that one extra line and that connection between the two to give you something to put into the calculator. That's it. Okay. All right on that one? Ready to try another one? Or is there something about that one that you think, oh, I'm not sure still? Excellent. Right, let's have a look at our next two options. Option 1, this one, this funny one with the words and like between and less than. Interesting, there's no probability sign there, yeah? Because most of them, they have probability signs. Like normally, oh, these are all like, are these not normal? There's a normal one. But yeah, anyway, normally there's probability signs and there isn't. So this is option 1. And then option 2 is this one here. There's this one, use the diagram to find the standard deviation. interesting, weird, unusual. This one looks fairly normal. We know the mean, we know the standard deviation, so it's not going to involve Z. So would you like this one here, number 1, which has got no probability signs and some weird wordy things and some data? Or would you prefer number 2, which has got a standard thing going on here, but then this funny question about what the standard deviation is by looking at the diagram? 2. You're all in unison. 2, 2, 2, 2, 2, 2. Okay, this one it is. Let's start. So we've got a picture and the mean is 178. And I'm not drawing this picture to be like, oh, let me explain it to you because you're students and I'm the teacher and I understand it. And I'm going to try and show you how it works using a picture. I'm drawing this picture because this is honestly how I do this question. So if I was jotting down the answer just so that I could tell you what I got, I'd still draw this picture because it makes the whole process quicker and cleaner, makes me less likely to go wrong, makes it obvious what's happening. So the mean is 178. 3 men aged 25 to 34, and this is ages. No, it's not. It's men aged 25 to 34. What's their height? 3 of them are chosen. What is the probability that all 3 have a height of less than 194? 194, this area here. But that's only 1 man. But we can work that out, 1 man's height. So we've got all these men, 25 to 34. We know the mean. What's the probability that one of them, chosen randomly, has a height less than 194? So we go into the calculator and we say that this is normal CD because we know what X is. It's a probability we're trying to find. And what's the instructions for that one? So it says lower, minus a million billion, upper, 194. Standard deviation, 8, mean, 178. For the standard deviation, it depends what they've given you. See, if it said the variance is 8, then the standard deviation would be the square root of 8. But because it says the standard deviation is 8, that's what the calculator wants. So if I was writing this in notation, it would be normal, mean, variance. And then what goes in the calculator is not the variance, it's the standard deviation, which is a bit annoying. And in the Z, in that formula as well, it's the standard deviation at the bottom, not the variance. Common mistake. Okay, so we've got this guy, we pick him out. The chance of him having a height less than 194 is 0.977. Now I pick another guy, the chance of him getting a height of less than 194 is also 0.977, then I pick another one. So what is the chance that these all 3 independent all have a height less than 194 is going to be you and you and you. Cubed. We're going to cube the answer. Answer is 0.933. Is that okay? So what they've done is kind of done a normal distribution and then like snuck in a bit of probability. The fact that the probability of this and this and this is the probability of that times the probability of that times the probability of that, so long as they're independent events. Okay, let's move on to the next one. So we know 2 facts about we know that 68% is within 1 standard deviation of the mean and 95 within 2 standard deviations and then all of it within 3 standard deviations. So if we have a look where all of it. It's an asymptote, so it never touches the ground, but where does it sort of touch the ground? So maybe there. So that's 142. What do you think? What about where it touches it up here? Maybe like there. So what I've done is I've gone from the mean and I've gone all the way forward to where the graph seems to touch the ground. It doesn't touch the ground. It's infinite. Yes, it's an asymptote. But what I'm going to is I'm going to the point, you know, I said the area under the whole thing, if you go 3 standard deviations, it's basically 100. It's 99.7. So it's basically 100%. So if you go 3 standard deviations forward, then you've basically got all the area. So the graph has got so low that it's basically touching the x-axis. It's not really, but the area underneath is so tiny, 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 tiny that it may as well be touching. So that there is 3 standard deviations. And that there is 3 standard deviations. You go backwards and forwards 3 standard deviations, you end up with all the data, more or less. And 190, I just kind of like, what do you think? Do you think it's about 190 where it touches, well, not touches, where it seems to touch the x-axis? 185, sorry, I read the scale wrong. Yeah. So this is 6 standard deviations. Now, using that information, would you be able to find out what a standard deviation is? Of course. All the way from 185 to, well, from 142 all the way to 185, that's 6 standard deviations. So if we do 185 minus 142, that whole distance is 43. 43 is 6 standard deviations. So 1 standard deviation is about 7.17. That's one way of doing it. Another way of doing it is to find the inflection points, because the inflection points are 1 standard deviation away from the mean. So let's try that. Where's the inflection point? This bit here is concave. This bit here is convex. Now, where is that sweet spot where it changes from concave to convex or vice versa? I think it's like there. So this distance is 1 standard deviation. The distance from the inflection point to the mean is 1 standard deviation, and then inflection point to the mean is 1 standard deviation the other way. So where's the other standard? There's the other one. Concave there, convex there, maybe here. Does that look about right? It's a guess. You've just got to do your best guess of where that inflection point is. So I'm going to guess that we're going from 155 up to 172. Let's see what I get when I do it this way. So this is 2 standard deviations, 155 to 172. 17. So 2 standard deviations is 17. So 1 standard deviation is 8.5. Now, which of those do you think is going to be closer to the correct answer? I mean, I would feel more comfortable giving my final answer as 7.17 because I'm more confident about where the graph seemed to touch the bottom than I am about where those inflection points were. So that's one reason. And the other reason is that even though there's going to be error every way that I do this, the more standard deviations that I'm dividing by, the more that error is spread out. So where I went wrong with the inflection points has only got 2 standard deviations to split that error between, whereas where I went wrong with where it touches the ground, that's 6 standard deviations. So I think my 7.17 is going to be better, but I'll tell you what the actual answer says. Yeah, so the answer is going to be basically between 2 things. So I'm just checking the answer, and what it says is something between, something between 6 and 7. I didn't get anything between 6 and 7. 70 minus 163. Oh, they think the inflection point is at 70. I'll do this one in red. They think the inflection point is here. And they've also guessed the mean. So they've guessed the inflection is 170. And they've guessed the mean is 163. So that is 1 standard deviation, but that's 7. Anything between 6 and 7, I would not get the mark for either of my answers. They've said that you can use the point of inflection is 1 standard deviation from the mean. So the point of inflection is at 170, the mean is at 163, that gives you 7. Or you could say 95% of the values are within 2 standard deviations, but I don't know how you would use that because there's no point to look for, or all of the values are within 3 standard deviations, which is what I did. No, I would not get the mark. That's sad, isn't it? Given that I know, well, I'd get 1 or 2 out of 3 because I have explained my method. Maybe if I saw, I mean, this is a screenshot. Maybe if I saw this on a piece of paper and it was big enough and I had a ruler and I could like be a bit more careful about looking for the inflection point. But yeah, that is the method. And then obviously the more precise you can get reading off the graph, the better. And then the final answer will be, it has to be between this and this. So I got unlucky with mine. Although mine rounds to 7, so maybe they'd let me have it. Okay. We are done with our normal distribution revision session. I think we did well. We've covered pretty much everything. We didn't do a normal approximation, but we did one with Z, one without Z, and one where you're using the common features. I would recommend now that you go into the content guide, look at the revision pack, have a look in the exam guide and traffic light those questions so that next time you go back to the revision pack, you know which ones you've done and not done. And then work your action hours within the context of the Tailored Tutors revision method, because that's really going to be what boosts your grade. You don't get better in maths, even though you feel like you will. You don't get better by doing loads and loads and loads and loads of questions. You get better by doing the same questions over and over and over until they're really, really fixed and simple. And that's what the TT method helps you to structure your revision into getting to that state. So within that context, go into the content guide, look at the revision packs, go into the exam guide, do your work, and any question at all that you've got, put it in the comments and we'll get back to you super duper quick and help you out with it. Hope you have a nice rest of the day and I will see you next week.